In this video, we'll talk about primary interrelated considerations and the tasks involved in memory tuning, how to use entries in proc sys VM and decipher proc mem info. We're going to talk about the use of VMstat to display information about memory, paging, I/O, processor activity, and a process's memory consumption. We're going to talk about how the OOM killer decides when to take action and selects which processes should be exterminated to open up some memory. Memory monitoring. Over time, systems have become more demanding of the memory resource, and at the same time, RAM prices have decreased and performance has improved. Yet, it is often the case that bottlenecks in overall system performance and the throughput are memory related. The CPUs and the I/O subsystem can be waiting for data to be retrieved from or written to memory. There are many tools for monitoring, debugging, and tuning a system's behavioral with regard to its memory. Tuning the memory subsystem can be a complex process. First of all, one has to take notes that memory usage and I/O throughput are intrinsically related, as in most cases, most memory is being used to cache the content of the files on disk. Thus, changing memory parameters can have a large effect on I/O performance, and changing I/O parameters can have an equally large converse effect on virtual memory subsystem. Memory monitoring utilities. Brief summary of a memory usage, VMstat, detailed virtual memory statistics and block I/O, dynamically updated. TMAP, process memory map. Let's take a look at it. Free-m. Proc memory info. The pseudo file proc mem info contains a wealth of information about how memory is being used. We do cat proc. See this file. So it is worthwhile to go through this listing and understand most of the entries listed in the table. Mem total is the total usable RAM, physical minus some kernel reserved memory. Mem free is the free memory in both low and high zones. Buffers memory used for temporary block I/O storage, cached. Page cache memory, mostly for file I/O. Swap cached memory that was swapped back in but is still in the swap file. Active, recently used memory, not to be claimed first. Inactive, memory not recently used, more eligible for reclamation. Active unknown, active memory for anonymous pages, inactive unknown, inactive memory for anonymous pages, active file, active memory for file packet pages, unavailable table, pages with which cannot be swapped out of a memory or released, locked, pages which are locked in memory, swap total, total swap space available, swap free, swap space not being used, dirty, memory which needs to be written back to disk, read back, memory actively being written back to disk. Unknown pages, non-file back pages in cache mapped, memory mapped pages such as libraries, SHMM, pages used for shared memory, slab, memory used in slabs, as reclaimable cached memory in slabs that can be reclaimed, as unreclaimed memory in slabs that cannot be reclaimed. Kernel stack, memory used in kernel stack, page tables, memory being used by page table structures. Bounce, memory used for block device bounce buffers. Write-back TMP, memory used by fuse file systems for write-back buffers. Commit limit, total memory available to be used, including over commission. Committed as, total memory presently allocated whether or not it is used. VM alloc total, total memory available in kernel for VM alloc allocation. VM alloc used, memory actually used by VM alloc allocation. VM alloc chunk, largest possible continuous VM alloc area. Huge page total, total size of the huge page pool, huge page tree, huge pages that are not yet allocated, huge page reserved, huge pages that have been reserved but not yet used, huge pages SERP, huge pages that are surplus used for over commission, huge page size, size of a huge page. Note that the exact entries you may see will depend on the exact kernel versions you're running. Okay, next. ProgSysVM. The ProgSysVM directory contains many tunable knobs to control the virtual memory system. Exactly what appears in this directory will depend somewhat on the kernel version. Almost all of the entries are writable by root. Remember that these values can be changed either by directly writing to the entry or using the sysctl utility. When tweaking parameters in ProgSysVM, the usual best practice is to adjust one thing at a time and look for effects. The primary interrelated tasks are controlling flushing parameters, i.e. how many pages are allowed to be dirty and how often they are flushed out to disk. Controlling swap behavior, i.e. how much pages that reflect the file contents are allowed to remain in memory, as opposed to those that need to be swapped out as they have no other backing store. Controlling how much memory overcommission is allowed, since many programs never need the full amount of memory they request, particularly because of the copy on write call techniques. Memory tuning can be subtle. What works in one system situation or load may be far from optimal in other circumstances. Take a look at it. As proc sys VM. I'll explain a little bit about its VM entry. Admin reserve 8 bytes. Amount of free memory reserved for privileged users. Block dump enables block I/O debugging. Compact memory turns on or off memory compaction, essentially defragmentation when configured into the kernel. Dirty backup group the bytes, dirty memory threshold that triggers writing uncommitted pages to disk. Dirty background ratio, percentage of the total pages at which kernel will start writing dirty data out of disk. Dirty bytes, the amount of dirty memory a process needs to initiate the writing on its own. Dirty ratio, percentage of the pages at which a process writing will start writing out dirty data on its own. There's a lot more here. You can do your own homework afterward. VMstat. VMstat is a multi-purpose tool that displays information about memory, paging I/O, processor activity, and processes. It has many options. The general form of the command is VMstat options delay count. If the delay is given in seconds, the report is repeated at the interval count times. If count is not given, VMstat will keep reporting statistics forever until it is killed by a signal such as Ctrl+C. If no other arguments are given, you can see what VMstat displays, where the first line shows averages since the last reboot. while succeeding lines show activity during the specified interval. VM stat 24. If the option -SM is given, memory statistics will be in MB instead of a KB. With the -A option, VMstat displays information about active and inactive memory, where active memory pages are those which have been recently used. They may be clean, disk contents are up to date or dirty, need to be flushed to disk eventually. By contrast, inactive memory pages have not been recently used and are more likely to be clean and are released sooner under memory pressure. Let's do VM -A 24. So memory can move back and forth between active and inactive lists as they get newly referenced or go a long time between uses. Do one more test here. Stat -A 24. To get a table of disk statistics, use the -D option. Do that. VM -D. If you just want to get some quick statistics on only one partition, use the -P option. VM stat P. Okay, let's move on. OOM killer. The simplest way to deal with the memory pressure would be to permit memory allocations to succeed as long as free memory is available and then fail when all memory is exhausted. The second simplest way is to use a swap space on disk to push some of the resident memory out of the core. In this case, the total available memory, at least in theory, is the actual RAM plus the size of the swap space. The hard part of this is to figure out which pages of memory to swap out when pressure demands. In this approach, once the swap space itself is filled, requests for new memory must fail. Linux, however, goes one better. It permits the system to overcommit memory so that it can grant memory requests that exceed the size of a RAM plus swap. Well, this may seem foolhardy. Many, if not most, processes do not use all requested memory. An example would be a program that allocates a 1 MB buffer and then uses only a few pages of the memory. Another example is that every time a child process is forked, it receives a copy of the entire memory space of the parent. Because Linux uses the call, copy on write technique, unless one of the processes modifies memory, no actual copy needs to be made. However, the kernel has to assume that the copy may need to be done. Thus, the kernel permits overcommission of memory, but only for pages dedicated to user processes. Pages used within the kernel are not swappable and are always allocated at request time. You can modify and even turn off this overcommission by setting the value of a process VM overcommit memory. 0 default, right? Permit overcommission, but refuse obvious overcommits and give root users somewhat more memory allocation than normal users. 1. All memory requests are allowed to overcommit. 2. Turn off overcommission. Memory requests will fail when the total memory commit reaches the size of the swap space. plus a considerable percentage, 50 by default of RAM. These factors modified. Changing process VM over command ratio. If available memory is exhausted, Linux invokes the OOM killer out of memory to decide which processes should be exterminated to open up some memory. There's no precise science for this. The algorithm must be heuristic and cannot satisfy everyone. In the minds of many developers, the purpose of the OOM killer is to permit a graceful shutdown rather than be part of the normal operations. In order to make decisions about who gets sacrificed to keep the system alive, a value called the badness is computed, which can be read from a prog PID OOM score for each process on the system, and the order of the killing is determined by this value. Two entries in the same directory can be used to promote or demote the likelihood of the examination. The object OOM ADJ is the number of bits the points should be adjusted by. Normal users can only increase the badness, decrease a negative value from OOM ADJ can only be specified by a super user. The value of OOM ADJ score directly adjusts the point value. Note that the use of OOM ADJ is deprecated. Okay, this is the end of this video. Thank you for watching. I'll see you in the next one. Bye for now.